Hi, and welcome to How to ROM-Hack Mega Man Legends 2. If you don't know me, I'm Hilltop. I'm a hacker and fan translator who has worked on a whole slew of PS1 and PS2 games. In this video, we're going to go through the entire process of creating a hack of Mega Man Legends 2 from a purely technical perspective. The work I've done on Mega Man Legends 2 in particular is that I've programmed the translation patch for Mega Man Legends 2 Episode 1, which was a Japanese exclusive prequel to Legends 2. The patch for this is now available, and you can download and experience the game now yourself. Now, you might think that if it's just a translation patch, then I probably didn't have to do much work to it. I mean, we're just editing text files, right? Well, not exactly. In order to do the kinds of edits that we were making to the game, you basically had to break the game down to its subatomic level and then have to rebuild it all over again. We'll be going over all of this in this video. This video assumes that you have some kind of programming and especially assembly programming background, or maybe that you've seen the other videos in my Developer Secrets series where I go over a lot of the techniques that are used here. A playlist will be in the description. We're going to take an approach that looks at the game as if it's kind of like an onion. We're going to approach the game from the outside and try to dig inward, layer by layer, until we get to the real core of the game, its real mechanical inner workings. The first layer that we're going to look at is purely from the outside, which is just looking at the files on the disk, the files that show up if you put the disk into your disk drive. Here are the files that show up, as well as a few directories. There's not much here at first glance, but we're going to be explaining exactly what each part of this does for the game. Some of these files we know we can basically ignore. They're not going to have what we're looking for, and what we're looking for in making a translation patch in particular are things like graphics, things like text, and things like code. First of all, this system.conf file, all it does is tell the PS1 which file to boot up when it launches, so that's something that doesn't have any interest for us. Then there's this znull.dat file. This is a purely empty file with no data in it, and it's just there to prevent disk read issues on the PS1. Then we have these XA files. These are CD quality streaming audio files for the PS1. They're not relevant to us today because we're not going to be editing any of them, but they are editable and they're standardized, so how-to guides already exist for XA audio. You can find it if you go looking for it. So if none of those are relevant, what actually is relevant for us? Well, the only files that remain are this slps_027.11. That's actually the main executable of the file. That contains a lot of the code that runs the game, as well as all of these .bin files. And those files could be literally anything. Bin is not a descriptor that gives us any actual useful information. It's just a meaningless descriptor to note that these files contain data of some kind. If we count up every bin file on the disk, there are about 350 of them. Now, this isn't enough to be every single file in the game if we count every single sound effect, every single texture, every single level. There's just not enough of them. This tells us that these bin files are actually packages that contain many files. They're also too big to be individual files. You'll note that some of them are like 500 kilobytes. Keep in mind that the PS1 only has 2 megabytes of memory, so 500 kilobytes is actually a lot. Our goal is to edit these bin files and eventually rebuild a working game disk. For reasons that we'll get into much later, these bin files that we come up with later might be a different size than the ones that they were originally. So we can't rely on a technique like in-place editing to simplify the rebuilding process. Luckily, there's a really handy tool called Make PSX ISO by LameGuy64 that makes rebuilding PS1 games pretty easy and intuitive. How it works is like this. First, we run the original disk image through dump SX ISO. That'll dump all of the files that are on the disk, but also create this build XML file. That build XML contains all the instructions to rebuild the disk after we have made the changes to it. Here's what that build XML file actually looks like. You'll notice that we have some disk information at the top here, things like the identifiers, the license, and some like track information. And then down here in the directory tree, we have all of the files, and you can see the bin files down here, the exe file here. And if we actually run this through make psx ISO, it will produce a working disk that's basically identical to the original game. But the problem is if we make any sort of change to it, for example, here I've put in just a single dummy sector. That is, I've basically moved the position of the files just slightly. What that does is cause the game to crash on boot. We're going to have to figure out why that is. This is a big problem for us because remember, we want to be able to move the files around because the files will be different sizes after we're done with them. So we have to solve this somehow. By all accounts, the game should work after I put in that one dummy sector. But why doesn't it? Well, it kind of goes like this. We expected that the game would be loading files based on their file name or based on their full path. For example, a game might ask to load a file given a string like this, which is the full path to this bin file. And if it did that, it would work. But that's not what the game is doing. It's doing something like this instead. It is specifying files based on their sector number. And that's something that it can do. It is allowed to ask for files from the disk according to their sector number. The sectors on a disk are numbered and basically correspond to its position on the disk. The first sector is at the very start of the disk, and the final sector is at the very end of the disk. In fact, if the game was being really fancy, it could even be doing something like this. This PS1 is really just kind of like a fancy CD player. If you tell it timestamps even, like timestamps on a CD, it'll still be able to load files that way. It's kind of weird to think about files being at a certain time signature on a disk, but this actually does work on the PS1. If the game is loading files based on their sector number, then we do know what those numbers are. We could open the disk in a program like Ultra ISO, and this LBA value for each of the files is actually the sector that it's located at. LBA, or logical block addressing, is just a fancy way to say the sector number. We think that these specific numbers are being stored somewhere in the game, hopefully in the main exe where we can look for it pretty easily. If we do search for these numbers, they do show up, like this. They appear to be part of this table where each entry is 12 bytes apart. So each entry in this table is 12 bytes, and they're each stored sequentially. First one here, next one here, next one here. These numbers are being shown in hexadecimal here and decimal here, but they do actually match up. I said that each entry is 12 bytes in length, but the file position is only 4 bytes. So what are these two other values? Well, green is the file size in bytes. We can figure that out pretty easily since file size and file position kind of go together, and it's easy to find one when you find the other. But what is yellow? I have no idea what yellow is. If I never edited it, the game never complained, so it didn't seem to matter. When we rebuild the disk, we need to update this table with the new LBAs and the file size for each file. But then there's kind of a problem there. How do we know where the files are going to end up before we have rebuilt the disk? Now, there's probably some clever solution that you can come up to solve this issue, but here's what I came up with. First, we would just build the disk once without updating the file table. Then I would run an analysis tool to find the new LBAs. And then I would update the file in the exe using this data. And then I would build the disk again with the updated file table in the updated exe. I didn't have to do any of this manually. It was just a part of the build process. That was all just layer 1. We can now rebuild the disk out of these files, but we haven't actually edited them at all yet. In layer 2, we're going to dive deeper into this onion and get to the individual files themselves. We know that the bin files have a lot of what we're looking for. They have to contain the textures and game scripting and text, basically by the process of elimination, because we know the other places didn't have them, so they have to be in these bin files. Now, before we said that these bin files were a package, so we're going to have to figure out how to unpack and then eventually repack them. Packages of files have to have some sort of directory or a table of contents that tells us where each individual file is in the package. Now, they could be a part of the bin file themselves in some sort of header, or they could be in the exe somewhere, or they could be in a separate nearby file. It all really just comes down to how that programmer just felt that day. It could be anywhere, really. Hopefully it's somewhere nearby inside of the bin. The first thing we're going to do is try to find some files so we can use them as an example. In CD-based games, individually loadable files have to start at addresses that are a multiple of 800 in hex. The reason for this is that 800 is the size of a sector on a disk. A directory might list a file's size and start position by its byte number or by its sector number, which is a unit that is 800 bytes. Or it could be using some sort of combination of these, but these are generally the values that we're looking for. We know that this file right here, this graphic file, starts at this address, and it's easy to tell that because this is a multiple of 800. 18800. Here I've pulled up the first 4 file starts in a bin package. We can kind of sort of tell that the size of the header is 30 bytes just by sort of looking at it and seeing that there's kind of a pattern between them. Purely by inspection, can we figure out how these file headers work? Can we look for any patterns here that sort of tell us where these file sizes or starts are? Well, you can pause the video and try to figure it out yourself. Here's how it works. If you round up the number in yellow to the next sector boundary, which is a multiple of 800, and then divide that number by 800, you end up with the number in red. That means that this yellow is the file size in bytes, while this red number is how many sectors this file takes up. It seems like we can use this to find the start of the next file, so each file basically points to the next one in the list. By following that chain, we can extract all of the files in a bin package. If you're really paying attention, you'll notice that this pattern doesn't actually hold up. It breaks on the last part of this chain. There's something going on here. Well, remember that this header itself has a size of 30. For some reason, they are not counting that as part of the file itself when calculating the size in sectors. So you have to round up only if the size of the header pushes the total size of the file over a sector boundary, over a multiple of 800. This is very weird. I don't know why they calculated it like that, but they did. What about the rest of the header? Well, it's pretty safe to assume that this pink value is the file type because of its association with cyan, orange, and green. You can see that this file type of 2 only includes cyan, a file type of A only includes none of them, and a file type of 3 seems to include green, cyan, and orange. We'll get back to what actually cyan, green, and orange are later. But the file size and sector size is really all we need to unpack these bins. We can set up a very simple algorithm that just looks at these files, scans it, extracts the file, and then moves on to the next one in the chain, and basically just repeats this pattern until it gets to the end of the file. It's really easy to unpack the bins now that we know how the header works. When we want to pack the files back together again, we just create a new header using whatever the new file size is and whatever this type specific info that we'll get to later is, and then just mash them all together one after another. So that was layer 2. That was just reaching the individual files. But now we have to actually identify what those files are. We have the individual files now, but what are they and how do we identify the ones that we're looking for? The text files, the graphical files, and the code. That's layer 3. We can save a lot of time for identification just by looking at the files in a data visualizer. Some hex editors like 010 will have a option to view the data through a visualizer. And if we do that, you start to see these patterns. Like, you know just at a glance that this is an audio waveform. This is an audio file. It always seems to have this wave pattern, and then these, every 16 bytes, it'll have a 0, which shows up as this black line every 16 bytes. Graphics, uncompressed graphics at least, that are in some sort of bitmap format, which they often will be for a PS1 game, you'll be able to actually see the shape of the graphic itself. Very, very handy. Compressed data, on the other hand, will typically look like nothing at all. It'll look like a mess. But code looks like a mess, but with some pattern to it. You'll notice that there are lots of zeros in code. That's because the NOP instruction, which shows up a lot in code on a MIPS processor, is actually 0000, which shows up as a thick black bar. And since code has a lot of it, you see a lot of zeros, which makes this image much darker than something that's more random, like the compressed data. After a certain point, when you've looked at a lot of data like this, you start to feel like, you know, that one guy in the Matrix. He doesn't even see the code. All he sees is blonde, brunette, redhead. You know this guy. If you're watching this video, you know who this guy is. But hold on, are we getting like way ahead of ourselves here? I'm used to being the first person to do any sort of significant hacking on a game, but this is a different situation. Mega Man Legends is actually popular. Have other people already looked at this and figured this out already? Am I wasting time here? If you look at the games that I've worked on, a lot of them are pretty obscure. Stuff that a lot of people, of course, have not worked on because they're generally Japanese exclusives. Over on the Mega Man Legends Station forum, some people have actually looked into this and have figured out a lot about how Mega Man Legends files are put together. A lot of what's already known is pretty relevant for us. For example, we know what the file IDs are for compressed and uncompressed textures as well as text. For example, we know that the uncompressed textures have an ID of 2, compressed textures have an ID of 3, and text has an ID of 1. What's also known is the header format for textures. So for file IDs of 3, we know what all these other file attributes are. For example, the CLUT X position, the color lookup table Y position, the pixel data X position, the pixel data Y position. These coordinates are in VRAM, by the way. I go over how graphics work on the PS1 in a different video that'll be linked below. The color lookup tables, width and height, and basically the image dimensions, the uncompressed size of the file, which actually does not correlate in this case to the sector size, and as well as something called the control block size, which is relevant to compression, as well as this one other file attribute here, which I never really actually figured out what it was, and I don't think anyone else figured out what it was. Just one of those, if you don't mess with it, the game doesn't complain, so you just leave it alone. What's also provided there is a decompression algorithm. The game uses a somewhat non-standard decompression algorithm that's loosely based on LZ. Um, if you really want to know how it works, you can pause the video, but I've gone over decompression and compression a lot of times in my other videos, so I won't be going into too much depth here. I said it was non-standard, but what I really meant to say is that it's terrible. This implementation of LZ is the worst in probably over a dozen games that I've cracked. The compression is done only in chunks, and every time a new chunk is started, a brand new static reference window has to be populated that only contains stuff from the current chunk. Basically, it builds up a useful reference dictionary and then there's just throws it all away multiple times throughout the compression and decompression and just starts with a blank one every single time, and it does this several times per file. It's really, really dumb. But because termination is also tied to these window pushes, like we can't actually use it in any sort of clever way to try to optimize it. We're stuck with this terrible system that they came up with. A working compressor does not exist. We have to come up with one. Now, I've already explained why this decompression algorithm is pretty weird. It has two termination conditions, which leads to the question, well, which one should you use and in what conditions? The reference window gets pushed up with a special pattern, and it might matter exactly how you do this, how you manage this reference window, because you have to do it manually for some reason. And it eventually ties into termination, is tied to how you push up the static window. Why it does this, I don't know. These problems cause very, very subtle wrinkles in the problem, and it ends up making writing a compressor kind of infuriating, because you'll think you'll have come up with something that should work, and if you feed it to your decompressor, it will work, but if you feed it to the game, it won't work. This is what I came up with, and this is what ended up working. Now you can pause the video again and look at it if you'd like. I won't be going over it in detail. We've pierced through another layer of this onion. We can finally look at actual text or image files. Because remember, we're trying to translate the game. It still feels like we are so far away from that goal, but we are getting there. We need to figure out how these text and image files work now that we've identified them. If you've watched my video on graphics, you should have an idea on how to tackle this. We can look at a graphic in a data visualizer and just at a glance figure out some things. We can find out the height, the width, where the color palette is, and where the data for the image itself starts. That sort of stuff is intuitive. Luckily, Mega Man Legends 2 doesn't do anything too weird with the graphics. It's just a little annoying in how it stores its color palettes separately from a lot of its images. So part of that is just trying to match up different color palettes with different images. But in the end, there wasn't that much of that we had to do. And once you've matched it up, you can program that into your image editor. Images that use the type 3 header have a lot of useful information for us about the color palette and pixel data. So the ones that use this file type make it easy to unpack these images and convert them to a PNG, and then later prepare it for reinsertion. The problem is not every single image uses this type 3 file type, so there is a lot of manual matching up that we have to do later on. So that was images, but what about text? Extracting text can be quite a difficult affair. It's a little bit nuanced when it comes to like older consoles like these. Often they won't be using any sort of standard encoding that you might be used to, like UTF-8 or SGIS. Those encodings take up too much space, and they might want to optimize that for these lower power systems. In our case, we have the font image extracted, so that actually gives us a lot of useful information to finding the text encoding. We can use a technique called relative searching to find the text encoding. Because we know the order that letters should be appearing in the encoding from the font sheet, we can plug that into a tool called monkeymore, and by using the order of the characters and some sample text that we extracted from the game, we can find the encoding itself. We place the text from the game into the search parameter, we put in the order of characters into this field here, and after we hit search, it should show up somewhere here. We have a hit at this address, and then the text encoding itself will appear here in the values. For example, this is saying that the space character is 4C, and that the exclamation mark is 0D, and so on. The encoding that it gave us makes a lot of sense, because if you actually count them up, the exclamation mark is the 13th character in the list. And if you count up all the way to the space character, you will find that it is the 4C position in the list, starting at the top left and going to the right. So if we want to edit the text, we have to really have a deep understanding of what files contain text and how those files work. This is an example of a text file. And if you want to figure out how it works on your own, you can pause the video here and try to figure it out. It's actually quite basic. So the file consists of a header and then the actual body, which are the text lines. The header contains relative pointers to each line of text in the file. How it works is like this. If you read this header, you'll know that the first 2 bytes contains the header size, but it's not just the header size, it's also a pointer to the first line of text in the file. There are 2 lines of text in this file, one at offset 6, one at offset 32, and then it terminates at 6D. So there are 3 entries in the header, but the final entry in the header is just the end of the file. So there are 2 lines of text in this file, one at 6 and one at 32. It seems like both of the lines of text end with FF, and that gives us a hint as to what the actual text terminator is. You'll see that from 6 to 32, the final byte is FF, and the final one at 6D is also FF. Interesting. Now that we know how the text encoding works and how the text files are structured, that gives us enough information to extract the text and create a dump that we can give to our translator to eventually have it re-injected back into the game. But when we extract the text, we get some odd results. Not everything that's in the text itself is text. For example, here's this line from this menu. In game, it just looks like this. It just looks like text. But the extracted line contains this weird bit at the beginning. What is this weird chunk of bytes at the beginning? That chunk is what's known as a control code. The text is there, but it's preceded by something that tells the game how to display that text. They're scripting commands that are built right into the text itself, and they affect it in many, many ways. Because there are so many ways, it's actually quite a difficult task to figure out how they all work. There are 2 paths that we could take to complete this task of figuring out how they work. We can reverse engineer all of the code involved in reading these control codes, or we can just kind of poke around in memory and sort of just feel it out. I'll show you how I just sort of poked around and figured it out. We're going to launch the game in a debug emulator, and we're going to get some text on screen, and then we're going to find that text in memory so that we can manipulate it. As we manipulate it, we gain information on the control codes and how they work, simply by modifying them and seeing what happens on screen. What's extra spicy about these control codes is that they actually have variable length. That means that each control code, in order to extract the text correctly, we have to find out how long each one is, and there are many of them. Because if we don't do that, we don't know exactly when the control codes end and the text starts. So we have to figure out the length of every single control code. We can put some text on screen like this that tells us the length of a control code, and then modify the control code that precedes this text and figure out how, and then just look and see how many of these characters get overwritten and removed. That tells us the length of the control code. The way these control codes seem to work is that they start with FB, and then the next byte is the type of control code that it is. For example, FB0E completely changes the line of text to whatever the next byte's ID is. For example, FB0E03 tells the game to switch this line of text to text ID 3. So the control code has this sort of formatting. We have to figure this out for every single control code, and as you'll see, there's a lot of them. This is how many there are. These are my notes that I took as I was figuring out how each one worked. Now you'll notice that there are a lot of question marks. I didn't actually need to figure out every single one. What I really needed to know is just how long they are so that I can extract the text correctly. Many of them I did figure out, like some of them are timers, some of them print button labels, some of them are counters, some of them tell the game what kind of text box to use, but some of them I couldn't figure out, and that's okay, because once again, as long as we don't mess with it, the game will probably not complain. There are some shortcuts that we can take when figuring out the length of control codes as well. If we see something like this, where we can clearly tell where the control code should end and when the text should start, like this little bit of text here, obviously this text is "Hello, Mega Man." So it's pretty safe to assume that this is the whole control code, because remember that control codes have to start with FB. And if there isn't another FB in here, we know that this is all one control code. Going back to that first example of the text in that menu, we now understand what this control code is and how it works. FB06 is a text box control code. It specifies the coordinates on screen to display the text and how wide and tall that text box should be. The control code FB06002800A81502 translates to display this text in a box at screen coordinate 28A8 and give it a max width of 15 characters and a max height of 2 lines. You'll notice that this coordinate system starts at the top left and not the bottom left that you might be used to. Coordinate systems in computer graphics tend to have the origin point in the top left. So the coordinate 28A8 is actually 28 across and A8 down. But there's something else in this piece of text. There are these 2 bytes at the beginning. What does that mean? Well, I don't really know. The game just puts 2 bytes at the beginning of every piece of text, and it seems like it has no effect whatsoever. Just another one of those, just leave them in so the game doesn't complain. So are we done with text? We can reinsert all the text and have it display in game. But no, we're not done because it looks terrible. We're editing a Japanese game here, and the original Japanese game had full-width monospaced text, and that really doesn't work well for English. The spacing of the text is not fixable by changing things like control codes or the text itself or the font. We have to go deeper into this game to fix this. But before we get to that, I have to explain something that we actually skipped in a previous section. Not all the text is stored in these type 1 bin files. Some of these text files are actually embedded in other files like the exe. This creates kind of a big problem because we want to be able to expand and change the size of these text files, especially because English is more verbose than Japanese. It usually takes up more space to store text in English than it does Japanese. This means that if we want to expand these text files, we have to be able to move them around. But the game has to be keeping track of these files somehow, and we have to figure out exactly how it knows where each of these embedded files are. Luckily, that's really easy to do in Ghidra. If we pull up the exe in Ghidra, which is where a lot of these text files are, we can just scroll to the start of the text file and it'll tell you where the reference is and what kind of reference it is. And there are two types of references. There are two types of ways that the game is keeping track of where these files are. The first type of reference is a pointer. It's literally just a piece, a integer that is a pointer to the file itself. So that's really easy to update because after we have moved the file to somewhere else, we can just give it the new address that it lives at. There's another kind of reference that's actually much more difficult to handle because they're hard-coded MIPS instructions that form the pointer instead of just storing the pointer. So there's a longer process to editing those references. Let's break down exactly how these code references work. If we follow the reference that Ghidra is telling us, we get to this instruction right here, this load operation. But where the pointer is actually being constructed is up here with these two instructions. First, the upper two bytes are loaded into this register, and then the lower 2 bytes are added to it. Even though the reference is pointing down here, if we want to update the pointer, we actually need to update these two instructions. If we look at the decompilation of this little piece of code, we get this little equation, which is actually pretty familiar because this is how the text files work. This is how the relative pointers work. First, we take the text ID and we multiply it by 2, and we get the offset of the header entry for that text line. And then we add it to the start of the file and then dereference it to get the offset for that text line. And then we add that to the start of the text file to get the offset to the text line itself. Here's a visualization of how these two instructions construct the pointer. First, the upper 2 bytes are loaded into v1, so we have the upper 2 bytes loaded, and then the lower 2 bytes get loaded after the add instruction, and now v1 contains the address of the text file. So there are two ways of editing these instructions. The first and most direct way is to actually use an assembler, and that would look something like this. Of course, here you would need to know ahead of time where the new files are going to end up, but we can just replace these instructions with something like a new load upper instruction and then an or an add after that completes the pointer. If we don't want to use the assembler, we can just edit the data directly. If we look at how these instructions actually are encoded, we can see that the immediate value, that is the parameter being given, is being encoded at the lower 2 bytes. You can see it really directly here, like the value 2F2C shows up as 2F2C here. So we can actually just modify this directly pretty easily with whatever our new pointer that we want is. There is kind of a wrinkle to this. If it's an add operation that you're editing, you need to check if the immediate value is higher than 8,000, because if so, this add actually becomes a subtract, and you need to add 1 to the upper 2 bytes to compensate for that. So that was quite a tangent, but let's get back to trying to make the text look good. we can put a load breakpoint on the text. And when we do that, and when that breakpoint triggers, when the text is being read, the emulator will break on this function. And here it is decompiled in Ghidra. You can see that there is a text pointer and it's being dereferenced right here. So this is the exact instruction where the emulator will break. We're looking for code that controls the font kerning here. So if we look at this in context, this function where it's being referenced, we can see that the return value for this function, which prints a single character, is the width of that character, and it's being set right here. All we have to do is come up with some way to make this value variable instead of static, and we have a variable width font. But before we start changing the code itself, we need to fix some things about the font. For example, you'll notice that the font is kind of smacked down to the bottom of the cell. How the game renders the text is these entire cells are being rendered one at a time, and the entire cell is being rendered. If we want a variable width font implementation, what we have to do is take each character and make it left aligned instead of center aligned. And then we have to make sure that it's being positioned vertically in a way that allows for both ascenders and descenders. For example, this G character originally does not extend below the baseline, and that's a problem, and that doesn't look good in English. So we have to move some stuff around. We have to move the characters around in the font itself. Now you might think in order to get better text rendering, in order to get a variable width font, that we change the cells that are being rendered. Instead of rendering the whole cell and printing them one at a time, we're going to print a just a portion of the glyph, and then that will solve the problem. Well, that doesn't actually solve the problem, because the game will print the glyph and then it'll move forward and then print another glyph and then move forward again, and it won't actually solve the problem. What we have to do is change the amount that the cursor is moving forward to the right every time a character is printed. The printing cursor as it stands always moves forward 12 pixels after every character. What we're going to do is we're just going to change that so that that's variable, and it only moves forward the width of the character each time a letter is printed. And that'll give us much better looking text. So here's the code that implements this change. We hijack a safe instruction inside of the glyph renderer, the character renderer, and it's going to jump to some code that we have written. What this code does is it looks at a table and it finds the width of that specific character that's being printed, and then sets the return value of that function to the width of the character. So obviously that means that we have to come up with this table that has the width of each and every single character. Luckily, that's not too difficult. In Python, I just have this function that gets the variable width font table. What it does, it just creates a bounding box around every single character, around every single cell, and that gives us a set of coordinates for this box. And we look at the width of the box that's generated for each and every single character, and we write that out to a table of all of the widths, and that's what's going to be read by our code in the actual game. You'll notice that we have to have a special exception for the space character, because we don't want our space character to be, have zero width. It needs to have a certain width, but the bounding box will give it a width of 0. So we have to create an exception for any empty characters. So now, are we finally done with text in the game? I mean, it looks really good, it looks really nice, and it's all being replaced. There's no Japanese text left in the game. Is there anything left?
そういうわけで、ロールとかいうヘナチョコメカニックを預かったわけなんだけど、どうなのよ、 仲間になるの？もしあなたがうんって言うなら、あの子はちゃんと家に返しておいてあげる。だから安心して今すぐここで仲間になっちゃいなさい。
Oh. Oh yeah. There's cutscenes. And these cutscenes don't have any subtitles. Yeah, that's gonna be a problem, isn't it? A big problem. This is no simple task. We have to come up with an entire system to detect what cutscene is playing and be able to trigger these subtitles at the correct time, with the correct length, with the correct everything. What does it even mean to do this? There's a lot that's involved. Well, remember those control codes? Well, they actually give us a system to create subtitles. What we discovered through testing are a set of control codes that help us craft a subtitle. We want a text box that appears and then disappears with a certain timing. So the control codes that are going to help us are as follows. We want to set the text speed to infinite, give it the right coordinates, give it the right text box style, and then the text box is of course going to include the actual text. And then in order to get a lifetime, a certain amount of frames that the subtitle is going to appear on screen, we have to then set the text speed to 1 and give it the lifetime in frames. And then put the terminator at the end and this little front buffer at the beginning, if you remember that. If we were to trigger these subtitles with that formulation, they look pretty good, and you can make them appear and disappear. But now we have to care about the timing. They need to appear at the right point in the cutscene, and we have to create some sort of file or something that the game is going to read to determine when to trigger each subtitle. The code will follow something like this. Every single frame, we need to determine if it is a frame that a subtitle should be triggered. And if so, it should trigger some corresponding subtitle. Simple in theory. The tough part is this. When should a subtitle be triggered? We want it to trigger at a specific frame during a specific cutscene. So we need to detect which cutscene is playing and exactly which part of the cutscene that we're in and how many frames that part of that cutscene has been going on for. Hopefully, we can identify some sort of memory address that gives us the right variables that tell us when we are at the right point in a cutscene. To find memory addresses, we can use a tool called RAM search, and BizHawk has a pretty good one. Now, this video, which is about a 20-minute demo, is long enough, and this is well-worn territory. I don't need to teach you how to use BizHawk's RAM search because tons of videos like this one exist already. But basically, it's a tool that allows you to isolate specific memory addresses that you're looking for, certain pieces of information. The ones we'd like to isolate are the cutscene timer, something that increments every frame that tells us how long a cutscene has been playing. Something like a camera shot ID, so we know exactly which camera shot we're in, like which part of the cutscene that we're in, and of course, which cutscene that we're in. As you watch this cutscene, keep an eye on those values on screen. The subscene ID, the cutscene ID, the shot ID, and the shot timer. These values, these memory addresses, are telling us everything we need to know to time a subtitle. If we're in cutscene ID 16, that will not change for this entire cutscene. But then those other values change accordingly as the cutscene progresses. These are the values that we're going to be scanning when we check to see if we need to trigger a subtitle. So like we said, we need to find a suitable place to inject this code now. This was not too hard. By poking around the text rendering functions, I found a place where the game basically checked if it needed to draw text on that frame, and it did that every frame, so it was the perfect place to inject this code. But triggering the right subtitle gets a little complicated. We need to create a brand new scripting format for these subtitles so that the game can read it every frame. We also need to inject new text files for these cutscenes. They have to be somewhere. So remember the text file format? We need to link the ID of a certain text line to a certain shot timer and value for each of these cutscene ID parameters. So we know what the game text files are going to look like, but what about on our side when we want to have editable text files that we can inject into the game? What are those going to look like? Well, I basically looked at the .ass subtitle format and made some changes to it. The subtitle format has lines, and each line corresponds to a subtitle. The information contained in it are things like the start time and end time, which I use to convert into a number of frames that's being used for the lifetime of the subtitle. A position value. In our hack, text dialogue subtitles can be either at the bottom of the screen or the top of the screen. And then the actual values of those cutscene IDs, like the cutscene ID, subscene ID, shot ID, and this last one actually didn't matter. It was some other value that I was tracking, but it ended up being the same for all subtitles. After that, of course, we need the shot timer, that's a very important number, and the actual subtitle text itself. We needed to turn that text file into a scripting file for the actual game to read. And this is what I came up with. Basically, each entry in this table is 8 bytes long. First, you have the cutscene ID, the subscene ID, the shot ID, and then that last value that didn't end up mattering. After that, we have 4 bytes for the shot timer, and at the very end of the table is a terminator that tells us that that's the final entry in the table. Notice that we don't link these to a certain text line ID because we don't need to. The first entry in this list corresponds to the first line of text in the text file, and so on and so forth. So we don't need to put in the text line ID for these entries. All that's left is to write the assembly to read this file and trigger the subtitle. Essentially, you can go through this algorithm that says we're going to look at each entry in the scripting file every frame, and if the values that are in memory line up with something that's in the table, then we trigger the corresponding subtitle. That's basically all it is. If you want to look at the ASM for this, it's on GitHub right now if you want to see it. And here it is in action. It looks pretty damn good if I do say so myself. Super clean. I wonder how many people even realize that these are all brand new subtitles. Of course, when we specify the dimensions and placement of the text box, there are some calculations that we have to do to place the text box in the correct position. For example, if you have a multi-line text box, you want it to still be centered at the general location. And that was the bulk of the translation patch that we made. There are some additional little tweaks and hacks that we had to do and problems that we needed to solve. For example, the game stores some of its large full screen images as multiple images, and we had to come up with a system to stitch these images back together again from these. For example, this image right here is actually made up of 10 different sub images, and that's annoying to work with. So we had to come up with a way to extract and inject this file as a full image and not in pieces. I also wanted to change the gradient color on the main menu, And surprisingly, that ended up being one of the most difficult things to do in this patch. The math involved in calculating the color at every single scan line is actually kind of complicated. I wanted to have a blue color that perfectly matched with the Mega Man Legends 2 logo, but I had to settle for basically this purple gradient, and you can see some of my failed attempts here at trying to come up with blue. A very weird thing to end up being the most difficult part of this whole affair. But our hack isn't just a translation. I got to restore some dev room stuff in our hack and made it accessible to the player. So for a long time we knew about these dev rooms. They were accessible by using a GameShark code. I wanted to turn this GameShark code into a part of the hack and allow the player to turn it on and off to enter the dev room. This is the cheat code that was listed as part of the hack. It's this number and then this parameter. What you put into these X values is the level ID. But how does this work? How does a cheat code work? What it does is it locks the memory address at this value to the parameter. So basically it sets this memory address to this value and it keeps it there. Because we know the memory address, this makes things pretty easy for us to find the piece of code that controls level loading. We could put a load breakpoint on that memory address, and when it triggers, it'll be at the part of the code that scans for the next level ID to load. So we can inject code there that instead of going to that level ID, it could check some condition and then go to the dev room instead if that condition passes. This is where it gets kind of tricky though. What condition do we want to check? We want to make this configurable by the player because we don't always want to go to the dev room when we load a level, only when the player wants to. But how do we do that? This is where the game kind of throws us a bone, because in the options menu, there is a furigana toggle. Now you might be wondering what that is. Furigana is the kana that appears above kanji in Japanese text. Games that are for younger audiences tend to include these to help younger children read. This has absolutely no use for us in English, so we can recycle this option to instead be a secret room toggle instead of a furigana toggle. Setting this option to on or off sets a flag in memory to 0 or 1 depending on the option selected. This is what we're going to scan to see whether or not to load into the secret room. After modifying the text and graphics here, it totally looks like I've added a new option to this menu where we can select to enter the dev room or not. Pretty sneaky. We've recycled what used to be used for one purpose, which was the furigana flag, and made it do something else. This is the kind of hacking that you want to be doing rather than creating things from scratch. Like, I could have spent a lot of time to add an option to this list, but this was just a lot easier. And here's the dev room in action. It was really cool to be able to add this to the hack, as this scene, this city here, has kind of been taunting players for a long time, since it was actually visible on the back of the CD case for Mega Man Legends 2, except there was no way to actually access it in the game. And that's all. That was everything that went into the translation patch for Mega Man Legends 2, Episode 1. This ended up being a very technically challenging project that required a lot of these creative problem solving and little tricks to get things working and to get things looking good. Overall, it took me about 6 weeks to go from 0 to 100 on this project for the programming side of things. And that was a pretty good time, I think, considering the amount of challenge that was involved. Thank you for watching this video. The work that I do is supported by my patrons on Patreon. If the work I do interests you and you want to see more hacks and translations, consider becoming a patron. This video went out 1 week early to patrons, and at the highest tier, you can also be added to the in-game credits for the hacks and translations that we produce.